Okay, gang, so buckle up your organic seatbelts because this video, it's very important. Unfortunately, a little bit on the longer side, but you really need to stick with me because if you guys nail down kind of synthesis strategy now, it's going to make your lives for the rest of OChem 1 and the rest of OChem 2 just infinitely better, okay? So you got to trust me on this one. Watch this video a couple times, and I swear it'll be for your benefit. Okay, so I want to start off by doing 2 complete the reaction problems to kind of get us warmed up, and then we're going to dive straight into synthesis problems. But let's do some complete the reaction first. Looking at my cheat sheet. Okay, so let's say I gave you guys ethyl Grignard, right, and little MGBR action. Could be MgCl, but I'm choosing to do MGBR. And let's say I put that together with this type of ketone, and I gave you guys a follow-up step of acid, right? Could be H3O plus, or I could have written H plus. They're both equivalent. Okay, so I hope by now you guys have done enough practice. You've done the last worksheet where you can look at this and say, okay, I know I'm going to attack with this carbon right here, and I'm going to attach to this carbon right there. So if I redraw the piece that had my carbonyl on it, this carbon-oxygen kind of thing, this group right here that was a carbonyl, it's now going to be an alcohol. And I hope you're saying that this carbon that we've dotted, I don't know if you guys don't have to do the dot system, I think it kind of helps a little bit though. You know, since there was a tack right here, we're now bonded to this asterisk carbon. So if I draw one line from the dot carbon, I'm now bonded to this asterisk carbon, and there's one carbon off that asterisk carbon, so there's my product. Okay? Let's do one more. Kind of a little bit of a role reversal type situation. What if someone gave you an arrow with acid over it, and they gave you this product? Okay? What if they gave you something like this? So instead of taking your 2 pieces, your carbonyl and your Grignard, sticking them together to form your alcohol product, they've given you the alcohol product, and now you kind of need to give the 2 precursors, right? So, and this is kind of a good lead into synthesis, but here's kind of the strategy I like to use. First, I look to whatever, I find the carbon that is directly bonded to the OH. Okay? I know that carbon used to be a carbonyl. And we can kind of look up here for reference, right? If we look at the carbon directly attached to the OH, he was the carbon attached to the carbonyl. So you kind of have a choice. Once you find that carbon, you get to make a cut. And that basically determines where your carbonyl is and where your Grignard is. So in my mind, if you can kind of see this with me, if I make a cut right here, can you guys see how this cyclohexane piece, if I just made this alcohol into a carbonyl, drawing green because the green's fun, right, that could be my carbonyl, this cyclohexanone, and this 3-carbon piece right here, that could be my Grignard, right? And now I have a question for you guys. Do you think I should make this Br or Cl? And my answer to you would be bromine. Because if I wanted to, right, put a halogen to then put magnesium on it, bromine would go there if I did free radical bromination. But do you see how I kind of, here, I'll erase that. So can you see how I made that cut? We're going to be doing that a lot, so hopefully that made sense. Okay? So let me erase this, and we'll get into our very first synthesis problem. So let's just dive into a synthesis problem. So here's how synthesis works. Some person, whether it be an exam or a practice problem or whatever, is going to give you starting material. 1 or more carbon pieces that you're allowed to work with to then kind of hit a target molecule over here, right? So kind of an example is this. If I gave you this 6-membered ring and this 3-carbon piece right here, I'd say propose an efficient synthesis given your starting material, propane and cyclohexane, to achieve the following target molecule. So this is actually what we worked with in that last complete the reaction problem. So if I gave you this, and knowing the reactions that you know, you'd have to you'd have to prove to me that you know how to make this. And believe it or not, it makes almost no sense until you do it enough, but working backwards is the easiest thing to do. Alright, it's called retroactive synthesis. Alright, so trust in me, let's start here and work our way back. So, my first step in any synthesis problem is I count my carbon pieces. Count your carbon pieces. Okay, so we have a 6-membered ring, and then we have a 3-carbon propane piece, right? So, we have 9 carbons over here. Let's see how many carbons are in our product. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so I know that seems pretty dumb, pretty redundant, but sometimes you have to use multiple pieces over here, and that'll be in the next synthesis problem we do. Okay, but let's start stepping this back. I usually like to go down and up just to kind of maximize my space, but essentially we're just going to literally transform these pieces into our final product. So, can you guys see that we obviously did a Grignard reaction as our final reaction, right? You can see we have evidence of an alcohol, and we've stuck carbon pieces together. So, this was the carbon. This is a carbon that's bonded directly to the oxygen, the OH, the alcohol. He was part of the carbonyl, right? Because a Grignard reaction is sticking a carbonyl and a Grignard together. So, I'm going to make a little cut right here. And I'm going to make this cyclohexane piece my carbonyl, and I'm going to make this 3-carbon piece right there my Grignard. So if I'm going to step an arrow back, remember, the final step of any Grignard reaction is adding acid. So I'm going to write H3O plus over that arrow. And what I'm going to do then is I'm going to draw my 2 pieces that I stuck together. My cyclohexanone, my cyclohexane ketone, and I'm going to stick together this MgBr 3-carbon Grignard. So you can see that if I attacked right there and then protonated, we would get that final product, right? So I just took it one step back. Okay, you're going to see why this is easy to do reverse as opposed to going forwards. So let's do this, because I can see this 3-carbon piece could easily become my 3-carbon Grignard, right? So let's again step it back. Alright, so I have a Grignard reagent. A precursor to a Grignard reagent is an alkyl halide, right? You obviously have to add in magnesium to an organic piece with a halogen on it. Right? So if I took this isopropyl bromide and added some magnesium, there's no doubt I would achieve that Grignard reagent right there. And now, if you kind of caught on to what I was saying in the last part of the video, the reason why I don't have MgCl here is because if I want a halogen on this middle piece, this secondary position, I don't want a free radical chlorinate, I want a free radical brominate, right? Right? So sometimes you have to think about using chlorine and bromine versus on where you want your Grignard to be. Right? If I wanted my Grignard here, Br, no doubt. But if I wanted my Grignard on the end, probably chlorine. Anyways, so we've made this piece, right? This part of our synthesis is done. So now we just need to kind of make this together, okay? So let's take this one step back. How do we know how to make ketones from what we learned in this chapter, this unit? Well, we can oxidize an alcohol, right? So, just for fun, let's try out Na2Cr2O7, sodium dichromate, and H2SO4. And that would give us a 6-membered ring with an alcohol. If we oxidize this alcohol, we would no doubt go to the ketone. Or we could use PCC, right? Same effect. Okay, now if we're going to throw it back to the first video of this series, now we need to make an alcohol, right? So, should we do this in an SN1 or an SN2 pathway? And you can see this is a secondary alcohol. So I think we should do an SN1 pathway. So let's say if I had a good leaving group, like this, I could absolutely toss some water in, right? sulfolysis would happen, water would swoop in and attack, and with a cleanup step, we'd have our alcohol on the six-membered ring. Okay, and now you can see how we're going to do this in one step. Throw it back to free radical bromination. Okay, so if that seemed fast to you, rewatch this again before moving on in this video. This is a relatively simple synthesis, so let's kind of go over the steps again. We looked at our final product and determined the big step, and it will most likely be the big step for now, is a Grignard reaction, right? That's the only thing we know how to stick carbon pieces together with. So we identified which piece should be our carbonyl and which piece should be our Grignard. That alone simplifies our problem, because now we have, instead of one big synthesis, we kind of have two mini syntheses, right? So then we easily handled our Grignard by saying, if we step this back from the magnesium step, we should have an alkyl halide, an alkyl piece with a halogen on it. Then we just did one step with free radical bromination, because we needed the bromine, we needed the secondary halide, not the primary, so we used bromine. Then we turned our attention to the ketone. We know that ketones can come from oxidizing alcohols, so we could have used PCC, but we used the sodium dichromate and H2SO4. From there, we knew we had to make an alcohol, and it's secondary, so we know SN1 is the best way to do that, from a good leaving group from an alkyl halide, which we could stick on with Br2, light, and heat. Okay, hopefully you caught on to that. In the next part, I'm going to erase this, and we're going to do a little bit more involved Grignard synthesis. And the best part is, if this made sense to you, all we're going to be doing is a double Grignard attack. All right, and you'll see why counting carbons is so important. Okay, so here's where counting carbons is extremely important. So let's count the carbons we start out with. 1, 2, 1, 2, 3. So overall we have 5 carbons with the initial things we've been given, right? The initial organic pieces we're allowed to use. And over here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they don't match up. That's interesting, right? That hasn't happened to us before. So here's what we need to do. Let's see what kind of combination of pieces we can use to kind of match up to 8. Sorry, math is hard. Okay, so we have 5 right here using one ethyl piece, or ethane piece, and one propane piece. But I think it's easy to see if we used 2 propane pieces and 1 ethane piece, we would then have 8 carbons. So let's keep that in mind. But again, let's start over here and work our way backwards, okay? So this definitely looks like evidence of not just 1, but 2 Grignard reactions, right? So let's do what we do best, and let's start at the end and work backwards, okay? So let's try and figure out that first Grignard reaction. So if I have an arrow and I have that last step of protonation, let's see where I can make a cut, right? And I have some options. But what I think I want to do is this carbon is definitely going to be the carbon that is going to be a part of our carbonyl that was attacked. However, what I'm going to do is let's kind of, I'll do this in red, nix this guy right here. So this is a 1, 2, 3 carbon piece, and this is a 1, 2, 3, 4, 5 carbon piece. Hopefully this makes sense. Take this 5 carbon piece and draw it right here, the carbonyl being on the, so if this is 1, 2, 3, 4, 5 carbons long, this carbonyl will be on the second carbon, right? 1, 2, 3, 4, 5. At the same time, I have now this 3 carbon piece right here, and you can see that I must have attacked with one of the terminal carbons, right? So that's where my Grignard should be. And if we're going to kind of look ahead, you can see I'm going to need Mg and then a halogen. So if I need halogen on the end of a carbon chain, I should probably use Cl. And if you can't see that far ahead, don't worry, you'll eventually see it as we step back. So let's make this piece while we can. It's a nice kind of confidence boost. Okay, So we know with Grignards, we're going to step it back one step. Magnesium, that would give us Right, by adding that magnesium, that means we must have come from an alkyl halide. And from there, right, we can see one step here. This would be Cl2 and light. And if you accidentally put MgBr here, don't worry about it, because if you took a step back, right, then you'd see bromine here, and then you'd say, oh, the most efficient way wouldn't be to use Br2 light and heat, because the bromine would go here. Then you can kind of see, I need to use MgCl to put a chlorine there. Okay, that part of the synthesis, done. Now we kind of need to figure out how we're going to make, this piece. So let's count our carbons. 1, 2, 3, 4, 5. Okay, so now this looks like just one of these and one of these, right? So let's kind of figure out where this came from. This must have been a synthesis, this must have been a Grignard reaction, right? And while it doesn't look like it, right? Because Grignard reactions produce alcohols. This is a ketone, right? Well, a little trickery. What if I said we could have done some PCC and the product of our Grignard reaction was this, but we must have oxidized it to prepare it for the second Grignard reaction, right? So here is the result of a Grignard reaction that we must have done. All we did was PCC it, or we could have done, Na2Cr2O7 and H2SO4. But now we have something we can handle. So again, let me find my dot carbon. He must have been the carbon attached to the carbonyl. Let me split this bond, because I think you guys can agree with me that this is a 2-carbon piece, this is a 3-carbon piece. That matches up with what we're given. And here's kind of a nice little, not trick, but a nice perk of doing syntheses well. So, step it back once from a Grignard, right, a step of acid. Here's the carbonyl we must have worked with, right, a 2-carbon aldehyde. And you see this 3-carbon Grignard? That must have been this MgCl. The best part is we already made an MgCl, so you don't even have to make this again. You can just let it be, because we've already proved we can make MgCl from our starting material. Okay, all we need to do is make this 2-carbon aldehyde, and we're done. So remember, aldehydes come from alcohols, and which oxidizing reagent do you use? The one that stops at an aldehyde, PCC. Right? So we must have had a terminal alcohol. Alright, now remember, this alcohol right here is primary. Is this going to be an SN2 pathway or an SN1 pathway? I hope you're sitting at your computer nodding your head being like, yo, that is an SN2 pathway. So remember, if we threw in some OH minus, and sorry, sometimes your arrows get a little wonky with syntheses and synthesis problems, but remember, that means we must have had a good leaving group to then attack with an SN2 pathway to produce this terminal alcohol. And what's great enough is we just have one more step, a little bit of Cl2, H nu, synthesis complete, drop the mic. Okay guys, so I have a ton of synthesis problems for you ready. I'm going to warn you, don't freak out about that last one. That is like a godly hard problem. If you can, that was more so like for you guys to look at. Hopefully, if you get it the first time, that's awesome. But, look at the solution, understand it. If you can do all those synthesis problems or understand them and reproduce them, you guys are well on your way to being organic badasses. Okay, so practice, 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 practice. I was awful at synthesis when I first started, but you have to kind of fail, learn from your mistakes by looking at the solution, honestly trying again until you get it right. Because it's really just a mindset, right? This took me a lot of practice, to kind of realize, oh, I need a halogen on the end. I should probably use Cl2. I need halogen in the middle, Br2. Make your alcohols the right way through either SN2, SN1. Okay, guys, this wraps it up for alcohols. So once you've done enough practice, I'll see you in the next series where we look at derivatives of alcohols with functional groups for ethers and another functional group called epoxides. See you then.